So this lesson is on using function notation. So we've been working with some linear functions written in slope-intercept form, which is the form y equals mx plus b. But as we move forward, sometimes you might see it written with this f of x symbol in place of the y, and this is called function notation. So by naming a function, then we can write it with this function notation. Now you'll see instead of the y, we have an f with the parentheses with the x, and we say that f of x. And this is basically just so that when we're finished with our function and we have f of maybe like 3, if we substitute in a 3, it will equal whatever the value of this equals, but we'll know then what the input and the output were, both. So a family of functions is a group of functions with similar characteristics. So, maybe they have the same slopes, or maybe they have the same y-intercepts, things like that. The most basic linear function in a family of all linear functions is called the parent linear function, and it's simply just of the form f of x equals x, which is basically y equals x, meaning the slope would just be a positive 1 and the y-intercept would be 0, or the origin. So we're first going to work on substituting and evaluating some functions. So here, what is the value of the function f of x equals negative 2x minus 7 when x equals negative 2? So if you're substituting in a number for x on the side with the function notation, that's really just letting the reader know what number you substituted in. However, you're actually going to do the calculation with the part of the function on the right. So you're just going to simplify that side. So negative 2 times negative 2 is positive 4. Positive 4 minus 7 is negative 3. So that tells me that f of negative 2 equals negative 3. So what does that mean? When x is negative 2, the y equals negative 3. Okay, so let's evaluate the functions here for the given value of x. So they're telling us they want us to put in this 7 here for the x. So f of 7 equals 0.3 times 7 minus 1.2. So 0.3 times 7 is 2.1. And 2.1 minus 1.2 is 0.9. So f of 7 equals 0.9. And the next question, we're going to substitute in this 4. So notice here there's a g instead of an f. Function notation can come in many different forms, just like variables. Different letters can be used for variables. They can for the function notation as well. So here g of 4 equals negative 2/5 times 4 plus 1/10. So negative 2 times 4 gives me a negative 8. And now I'm going to add that to my 1/10. Now, adding fractions, basic here. 5 times 2 is 10. We need that common denominator. Then this is going to be a negative 16. So then g of 4 equals negative 16 plus 1 is negative 15, and that's over that common denominator of 10. And so then if I simplify this, I'm going to have g of 4 equals negative 3 over 2. Okay, so this is just some practice that we can do if we want to evaluate functions for the following different inputs. So you could evaluate one function, like I could evaluate function 3 here, the number 3 here, for all 3 of these. So I'll just show you for a couple of these examples. I'm not going to do all of them. So if I wanted to first maybe find this function here for negative 3, so I would input that negative 3. Then I would work it out. So f of negative 3 equals, that's negative 45 plus 4, which would be negative 41. I could also evaluate this function for a 0. So 15 times 0 plus 4 simply equals 4. I could also evaluate this function for the positive 2. 15 times 2, which is 30, plus 4 would give me 34. So you can see it's just like doing an input-output table, essentially. If we had these values for our domain or inputs, and then the negative 41, the 4, and 34 would be our outputs. Okay, so let's do a couple more, but we'll use the fractions just because we always need extra practice there. So I'm going to use the x equals negative 3 for this problem. I'll do x equals 0 for number 10, and x equals 2 for number 11, just to give it an example for each. So here we have s of negative 3 equals 4/5 times 3 minus 2. So again, 4 times 3, this would be 12/5. And I'm going to be subtracting 2, which is 1 over 1. So I need a common denominator of 5, which will make this a 10. So now when I subtract those two fractions, 12 minus 10 leaves me with 2/5. Now for the next example, we're putting in x equals 0. So I'm going to do d of 0 equals negative 5/3 times 0. Of course, anything times 0 cancels out, and so d of 0 equals 4. And in the third example, h of positive 2 equals 3/8 times 2. Now that can actually cross reduce or cancel a little bit, so I get h of 2 equals 3/4 minus 6, which is really over 1. So this is where I want to make my common denominator. And now I can finish up by subtracting those two fractions. 3 minus 24 would be negative 21, and that would be over that common denominator of 4. Okay, so now that we've seen how we can evaluate these functions by substituting in a value for x, now we're going to go over how do we find x if we know what the function is equal to. So here it says for the function f of x equals negative 3x plus 2, find the value of x so that the function equals negative 13. So it's essentially like they're giving us the output and they want us to find the input. So for example, we would substitute that negative 13 in place of the f of x, which is really like your y value, and then you would get the x by itself simply by using your inverse operations. So subtracting the 2, dividing by the negative 3, and so forth. So let's take a look at a couple of those. So for number 15, for example, it's telling me here, find the value of x so that the function has the given value. So I'm going to substitute this 4 in, or I'm going to replace my g of x with that 4. And now I'm just going to use my inverse operations to get this x here alone. So I'm going to add my 3 to both sides. That will give me 7. And then I would have to multiply both sides by the reciprocal, which is negative 2. And I'm going to get x equals negative 14. So g of x equals 4 when x equals negative 14. So let's try it for this one. Again, we're going to plug that negative 13 in, not in for the x, but in for this entire function, because we want the whole function to equal negative 13. Now I can solve for my x. So I'm going to add the 3, which is going to give me a negative 10. Divide by 5, and x would have to equal negative 2 in order for the function to be equal to negative 13. So just a couple practice ones, but I'm going to go on to the next page and do a couple there instead. Okay, so let's take a look at these two. All right, so for this one again, that 3 is going to go in for the solution of the function, and then we're going to solve for the x value. So then you're just solving a regular equation using your inverse operations. I have 12 equals negative 4x, divide by negative 4. That gives me x equals negative 3. Okay. All right. All right, so for the next example, we're going to graph the function, and then we're going to compare it to the graph of f of x equals x. We're going to use this as our parent function. This will be our parent function, and then we'll kind of look at it in relation to that. Okay, so f of x equals x, which I'm going to graph in red here, is, remember, going through the origin with a slope of positive 1. This is the most basic linear function. This one here I'm drawing in the red. So all other functions are really just this manipulated in some way. So that's what we're asking here. So if we know that the parent function is f of x equals x, and that's this one here I just did in the red, that means that my slope is 1 and my y-intercept is 0, right? Now, the function for this particular question, m of x, was 1/3 x. And then notice this one also has an origin, or a y-intercept going through the origin, but this time the slope was 1/3. So this one, while they're still a positive, they're still going through the same y-intercept. This one is not quite as steep, so we would say it's less steep than the parent function. So you can see this one here in the blue is like a little bit slower of an increase because it's only got a slope of 1/3 as opposed to the parent function, which has a slope of 1. All right, so again, I'm going to start out with my parent function. Okay, this is my parent function here, and I'm going to put that in the red. So remember, my slope is 1 and my y-intercept is 0. Okay, now the function for the problem here, n of x, that's this one, is x minus 2. So this one also has a slope of positive 1, but this time the y-intercept is negative 2. Now you'll notice, since the slopes are the same here, you can see that these are parallel lines. They're not the same line because they have different y-intercepts, but they do have the same slope, making them both parallel. Okay, so this time says graph the function, compare your function to the graph of f of x equals x. So again, my parent function, I'm just going to continually use that same parent function. And then this time, I'm going to graph this one here. So I'm going to go to negative 4, and then up 1 over 1, up 1 over 1, and so on. And just like the last problem that we saw, since the slopes for both of these would be the same, but the y-intercepts were different, these would be parallel. Okay, so let's take a look at number 29. Now this time I have my parent function right through here. So this is f of x equals x. So now if I want to graph this one, notice this one has a b, or a y-intercept of 0, but the slope is 5 compared to the y-intercept of 0 and the slope of 1. So this one we would have to go up 1, 2, 3, 4, 5 over 1. So it looks something like that. Or we'd be off the graph down here. Now you can see this graph, it's still tilting on a positive direction, but m of x is much steeper than the parent function, and that's because the slope was a much larger number. So the larger that slope value is, it's going to make the line or the graph steeper. All right, now here's one with a fraction. So again, I have my parent function that has a slope of 1 and a y-intercept of 0, and I'm going to graph that here in the red. And then I'm going to do this graph here in the blue. And so this one is the slope of 1/3, but my y-intercept is 0. So notice that they have the same y-intercept, but this graph is going up 1/3, which is going to give it a much shallower slope. So we can say it's less steep, or you could say flatter or shallower, or however you want to word that, than the parent function. Now let's look at number 32. So if I look at 32, this time my parent function's still the same one, slope of +1 and going through the origin. Okay, but this time I have a -2x. So my slope is a -2 and my y-intercept is the origin. So the origin's still the same, but this time I'm going to go down 2/1, down 2/1. So notice this one does look a little steeper because 2 is a larger value than 1, but it's a -2, which actually changes direction. Now it's going downward instead of upward. So when you have a slope that's negative, that changes the direction of the line, but the number itself, the value, the absolute value of that number will tell you how steep or shallow the line is. Okay. So let's take a look at a couple of these examples here. So it says the number of hours people in the United States playing video games each year from 1998 to 2001 can be modeled by this function, where x is the number of years since 1998. So I like to think of, I have my x and my y, or in this case, my y can be written as my f of x, right? So the year 1998, we will make that kind of the starting point, which is year 0. And then 1 year later would be 99. And then 2 years later would be 2000. And then 1 year after that, or 3 years totally later, is 2001. So if I'm plugging into that function, f of x equals 11.9x plus 46.4. Now it's already in this slope-intercept type form, so you could graph it by doing 46.4 over here on the y-axis or estimating it, but then you'd have to try to do going up 11.9 and over 1, which is a little bit tricky because of the large increments and the decimals and things. So a lot of times I just like to plug the numbers in. Now, if I plug in 0 for x, then I'm just going to be adding 11.9 plus 46.4 and so on. But I'm going to show you a cool way you can get all the points in your graphing calculator. So if you go to y equals, and you type in 11.9x plus 46.4, and then you could press graph and you'll get a picture of your graph. But if you go to second table or second graph, it'll give you your table. And notice I was starting at 0, right? So 46.4. Oh, I think I missed something here. Okay. All right, so 46.4, then 58.3. So we got 46.4, 58.3, 70.2, and 82.1. All right, so those would be those values there. So if we're going to graph it, I have the 0, 46.4, then I'm going to go 1 and 58.3, then 2 and 70.2, and then 3 and then 82. So you can kind of get an idea. All right, so remember your domain is your x values, and that here would be basically x is going to be greater than or equal to 0, but less than or equal to 3, which means that we actually want to just graph to here. And then my range is my y values, and the lowest y value is 46.4. And the largest one that we could have is 82.1. Because remember, there was like a limit here. It only went from 1998 to 2001. Finding the value of f of x when x equals 2. Well, we've already done that in this chart here. We know that it's 70.2. So that means that if it's the year 2000, or 2 years since 1998, then we know that this is the amount of hours people are spending with the video games. And then finally, find the value of x. So f of x equals 60. Well, since we don't have exact 60 on our f of x side of the chart, we know it's going to be somewhere in here, right? So 1 point something, but you can substitute that 60 in like we did earlier in the notes, and then solve for that x value. So this would be, I think, 13.6 equals 11.9. And I believe when you divide, you're going to get somewhere around like a 1.1 or so for that one. That's it.